Welcome to BrainOmega. Today we're starting at the very foundation. What is natural language processing, or NLP? NLP is all about using computers to work with human language, the words we speak, write, and even type into search bars. Imagine you're looking at customer reviews on a travel booking site. For you and me, understanding a review like "the hotel was clean and close to the city center" is easy. We immediately get the meaning, the sentiment, and even the subtle details. But for a computer, this is just a string of characters. That's where NLP comes in. It helps computers make sense of language so they can do things like analyze reviews, answer questions, or even translate your travel plans into another language. Every time you talk to a virtual travel assistant, get automatic recommendations for flights, or see hotel reviews summarized for you, you're using NLP in action. Let's take a quick look at how computers handle data. If you run a travel site, you probably have lots of tables of data, things like ratings or prices. Computers love numbers. Calculating the average hotel rating? No problem. But look at the review column. Suddenly, it's not so easy. Words are messy, full of context, emotion, and even sarcasm. For a computer, "this hotel was the bomb" could be confusing. Is that good? Bad? Explosive? Natural language processing is the set of tools and techniques that lets computers work with this complex, rich text data, turning it into something useful and meaningful. Where does NLP fit in the world of artificial intelligence? At the very top, we have AI, computers doing things we once thought only humans could do. Below that, we have several branches. Computer vision helps computers see and recognize things in images. Think of scanning your passport with your phone. Machine learning lets computers learn from experience, like predicting flight prices based on past trends. NLP is all about language, interpreting and generating text, just like a human. Whether it's answering your travel questions or sorting reviews, NLP is the technology that helps computers understand and respond in natural language. In a travel booking company, a data scientist might analyze sales numbers, website clicks, and yes, even text data like customer reviews. That's where NLP is so valuable. With the right techniques, you can turn thousands of raw reviews into actionable insights. What do travelers love most about your hotels? Where do they see room for improvement? NLP helps you find the answers hidden in the words. All right, let's see this in action with a little code demo. Imagine you're running a travel booking website. You have a table of hotel ratings, prices, and reviews from your customers. Let's load up some example data using Python and pandas, which is a super popular library for working with tables of data. You can see here we've got 4 hotel stays with a rating, a price, and the customer's review text. Now, computers absolutely love numbers. Let's see how easy it is for a computer to calculate some stats. No problem at all. Calculating the average rating and the average price is super easy for a computer. But now let's try to do the same thing with our review text. What if we ask the computer to give us the average review? Oops! The computer throws an error because it has no idea how to take the mean of text data. For us, looking at the review, "this hotel was the bomb," is clearly a positive thing. But for the computer, it's just a string of characters. No meaning, no understanding, just confusion. And this is exactly why NLP is needed. Natural language processing gives computers the tools to work with words, not just numbers. With NLP, we can teach computers to figure out if a review is positive, negative, or even sarcastic. We can summarize reviews, analyze trends, or build chatbots to help customers in real time. The history of natural language processing is full of excitement, setbacks, and breakthroughs. Let's walk through the major eras, starting in the 1950s and traveling all the way to the present day. We begin in the 1950s, where the very first attempts at using computers for language focused on simple rules and pattern matching. One famous example is the Georgetown IBM experiment, where a computer was programmed to translate Russian into English using just a small set of words and some handwritten rules. This was the first machine translation demonstration, tiny by today's standards but groundbreaking at the time. Then, in the 1960s, something even more interesting happened. The first chatbot, Eliza, developed at MIT, could hold a simple conversation by matching patterns and giving rule-based responses. It was like talking to a computer therapist, sometimes a bit silly, but people were amazed. These early efforts were exciting, but they hit a wall. Language is messy, and simple rules just weren't enough. Researchers realized if computers were ever going to understand language, they'd need more than just patterns. That led to the next era, traditional NLP, starting in the 1980s. Suddenly, computers were getting more powerful, and new mathematical tools called probabilistic and statistical models entered the scene. Instead of just following rules, computers started to use data and probability. This meant they could analyze huge collections of text and start to spot patterns, like which words tend to appear together or how often certain phrases pop up in travel reviews. In the 1990s, a landmark resource appeared, the Penn Tree Bank. Linguists hand-labeled millions of words, creating a goldmine for researchers to build and test new models. At the same time, machine learning began to revolutionize the field. Now, instead of just writing rules, researchers trained models to actually learn from labeled examples, such as which reviews are positive or which questions customers are asking about hotels. By the 2010s, a new revolution was underway: deep learning. Instead of designing features and rules by hand, computers began to use neural networks, complex mathematical models that could learn directly from raw data. Recurrent neural networks, or RNNs, and later LSTMs, helped push NLP to new heights. Pow! But the real game changer arrived with transformers. Models like BERT and GPT could handle language in ways never seen before, generating realistic conversations, summarizing reviews, and even answering travel questions with incredible fluency. Today, these large language models are at the core of modern NLP, and research is moving faster than ever. So, to sum up, early NLP was all about rules. Traditional NLP was about statistics and machine learning, and modern NLP uses deep learning and transformers, each step built on the last, making it possible for travel sites, apps, and virtual assistants to handle language in ever more human-like ways. Now let's bring history to life and build our own version of an early NLP chatbot, just like Eliza, but specialized for travel bookings. This little bot is rule-based. That means it doesn't really understand what you're saying. Instead, it's like a super basic call center menu. It looks for certain keywords and then gives a fixed reply. Let's walk through the code. First, we have a function called Travel ElizaBot that takes whatever the user types and turns it into lowercase. This makes it easier to match words, no matter how they're typed. Now comes the heart of the bot, a set of if statements. Each one checks if the user's message contains a specific word. If you mention book or reservation, the bot says, "I can help you book your trip." Where do you want to go? If you type cancel, it gives a polite but canned response. "I'm sorry to hear that you want to cancel. Which reservation should I look up?" If you ask for a recommendation or say suggest, the bot asks, "What type of destination are you interested in? Beaches, cities, or mountains?" There are also responses for greetings like hello or hi, for saying thank you, and for asking about price or cost. If none of these words appear, The bot doesn't know what to do, so it falls back to, "Can you please tell me more about your travel needs?" Say, now at the bottom, we have a little conversation loop. The bot starts by greeting you and then waits for your input. If you type exit, quit, or buy, it ends the chat. Otherwise, it uses our rule-based function to generate a reply and prints it out. Let's try it out. I'll type, "Can you recommend a hotel in Paris?" The bot recognizes recommend and asks what type of destination I like. If I say I want to book a flight, it gives the booking response. If I ask, how much does it cost? So, it knows I'm asking about price. But if I type something it doesn't expect, like, "What's your favorite travel memory?" the bot can't handle it and just ask. Let's take a guided tour through the wide spectrum of NLP applications and techniques that we'll explore together in this course. You'll notice that NLP strategies can be grouped into two big families: classic approaches, which laid the groundwork for language technology, and modern methods, which are powering today's most advanced AI tools. For each one, we'll see how it's used to solve real-world problems in the travel industry, like understanding reviews, sorting messages, and even recommending trips. Starting with classic NLP, we begin with rule-based pattern matching. Here, computers simply look for specific words or phrases, following hard-coded instructions. Imagine a system that automatically flags phrases like "excellent stay" or "poor service" in hotel reviews. This is the essence of rule-based methods: quick, simple, but not very flexible. The next technique is machine learning with logistic regression. This method learns to sort text into categories based on examples. For instance, by showing the computer labeled emails, some are booking requests, others are complaints, it can automatically learn to separate new incoming messages and route them to the right department, saving time and improving customer service. Then we move to unsupervised clustering methods, such as k-means or LDA. Unlike rule-based or supervised techniques, clustering groups similar texts together without any prior labels. In a travel business, this could mean automatically discovering themes in guest feedback like "clean rooms," "helpful staff," or "great location," without anyone needing to manually sort thousands of reviews. Transitioning to modern NLP, we reach the world of deep contextual models like BERT and other attention-based architectures. These models don't just look for keywords, they truly understand the meaning and context of each sentence. They can pull out specific information, such as guest names or travel dates, from a messy chat conversation, making it much easier to fill out booking forms automatically. Another leap forward comes with encoder-decoder models, such as T5 or BART. These models are masters at transforming or summarizing text. For example, they can take a lengthy guest review and generate a concise summary, giving hotel managers quick insights without reading every word. Generative models like GPT are the creative writers of the NLP world. Not only can they answer travel questions and write emails, but they can also craft entire personalized trip plans based on a customer's interests, producing content that sounds naturally human. Finally, there are embedding models like Mini-LM, which take language and turn it into numbers that computers can compare. This allows a travel site to recommend similar destinations or group together articles and reviews about related topics, making search and discovery a breeze for users. As you can see, every one of these NLP techniques, from classic pattern matching to modern generative AI, serves a practical role in the travel business, transforming unstructured text into valuable insights and powering user-friendly digital experiences. By understanding each approach and where it fits, you'll be equipped to build smarter tools for your own applications and understand the magic behind the technology you use every day. We're going to explore how approaches to natural language processing have evolved generally over time in terms of architecture, from early methods to today's most powerful techniques. Let's begin with one of the earliest and most influential, the TF-IDF approach. TF-IDF, which stands for Term Frequency Inverse Document Frequency, is a classic statistical technique that helps us understand which words are most important within a single document compared to all the other documents in a collection. Using TF-IDF, we can convert words and sentences into numbers, creating a mathematical representation of language that computers can process. Once our text data is in this numerical form, we can use machine learning methods like the naive Bayes classifier to categorize reviews, messages, or emails. We can even combine TF-IDF with clustering algorithms like K-means, which allows us to automatically organize large collections of travel reviews or customer feedback into common topics. However, TF-IDF and similar approaches have their limits. They only pay attention to how often words appear, ignoring the order of words and the actual context in which they're used. This means these methods can't fully capture the meaning of sentences, and they certainly can't generate new text like answering a question or writing a summary, things we expect from modern NLP systems like ChatGPT. As computers became more powerful, thanks in part to advances in graphical processing units or GPUs, researchers were able to train deeper neural networks such as recurrent neural networks or RNNs. RNNs are better suited for handling sequences because they can pass information from one word to the next, allowing them to model temporal relationships in text. But RNNs also have significant drawbacks, especially when it comes to learning long-range dependencies in language. They often suffer from problems like vanishing or exploding gradients, which makes training these networks extremely difficult. To overcome these issues, the long short-term memory, or LSTM architecture, was developed. LSTMs are a major breakthrough because they are much better at remembering important information over longer text sequences and help prevent vanishing gradients. However, even LSTMs have challenges. They're still slow to train, use a lot of memory, and struggle to capture relationships between words that are far apart in a sentence or paragraph. They also can't take full advantage of parallel processing since they process text one step at a time. This brings us to the modern era of NLP and the rise of the transformer architecture. Transformers, thanks to their self-attention mechanism, can model long-range dependencies in text much more effectively and efficiently than previous approaches. They can process entire sentences or even documents at once rather than word by word, allowing them to capture the global context and relationships between distant words. This makes them ideal for a huge range of tasks, from classifying travel reviews to clustering customer feedback to powering advanced applications like ChatGPT that can generate natural, human-like language. So, as you'll see in the upcoming chapters, our focus will shift towards understanding how transformers work, step by step, and why they have become the foundation for the most powerful NLP applications today. Let's dive in and unlock the secrets behind this groundbreaking technology. When starting an NLP project, the very first thing you'll do is define your objective. It's just like planning a journey. You need to know your destination before you can set out. For example, imagine you're working with a travel company and your goal is to automatically identify and summarize guest complaints from thousands of hotel reviews. Getting this objective crystal clear will guide every other step you take. Once you know what you want to achieve, the next step is to collect all the text data you'll need. For a travel business, this might mean pulling in recent reviews from your booking platform, exporting chat logs from your customer service chatbot, or even gathering feedback from survey responses. Sometimes you'll combine data from different sources to get a complete picture of what your customers are saying. With all your raw data in hand, it's time to clean things up. Real-world language data is often messy, filled with typos, duplicates, missing information, or strange formatting. At this stage, you'll remove errors, standardize the format, and make sure you're only working with high-quality, useful text. Now comes the step that's unique to NLP projects: text pre-processing. Human language is full of quirks, so before a computer can understand it, we have to prepare it carefully. This often means converting everything to lowercase, removing special characters and common words that don't add meaning, like the or at, and breaking sentences into individual words or phrases. You might also want to reduce words to their base form, so traveling and traveler are recognized as the same root. This turns a messy review like "I absolutely loved the breakfast" into a simple, analyzable format like "love breakfast." With clean, pre-processed text, you're ready to explore your data. This is the part where you get curious. What words come up most in negative reviews? Are there clusters of complaints about cleanliness, noise, or staff behavior? You might make charts, word clouds, or group feedback into topics, helping you spot patterns that will guide your next steps. Next, you'll build and refine models to answer your original question. Maybe you train a classifier to label reviews as complaints or compliments, or use clustering algorithms to discover hidden themes in guest feedback. You might even experiment with different types of machine learning models, from straightforward logistic regression to cutting-edge transformers, adjusting your approach based on what works best for your specific data. The final step is to share what you've learned. This could mean presenting your findings to hotel managers, building a dashboard to track trends in real time, or even deploying your model so it automatically alerts staff when a new complaint is detected. The value of your work comes from turning language into clear, actionable insights that others can use. Remember, this process is rarely one way. As you go through the workflow, you'll often find yourself looping back. Maybe you discover a new kind of feedback you hadn't considered, or your model reveals a data quality issue you need to fix. This kind of iteration is normal and helps you build robust, real-world solutions. In summary, the NLP workflow is all about moving from messy raw language to valuable, data-driven answers step by step. Whether you're sorting reviews, building chatbots, or extracting key details from messages, following this structured approach will help you deliver real impact in any business, especially in fast-moving industries like travel. Now, let's dive deeper into the crucial phase of text pre-processing, an essential bridge between cleaning raw data and modeling it effectively. Think of this as preparing your raw guest reviews or booking messages to be machine-ready so that the computer can actually understand and analyze them. The first step in this preparation is lowercasing. This means converting every letter in your text to lowercase, so words like hotel and hotel are treated as the same. It may seem simple, but it avoids confusion and redundancy in later analysis. Next, we remove special characters. Customer feedback often includes punctuation marks, emojis, or other symbols that don't add meaning for our model. Using tools like regular expressions, we strip out these characters so the text is cleaner and easier to process. After cleaning, we move on to tokenization, breaking down sentences into smaller pieces, usually words or sometimes phrases. For example, the sentence "great location and friendly staff" becomes a list: great, location, and friendly staff. This is the basic unit the computer works with during analysis. To reduce complexity, we apply stemming or lemmatization, which means converting words to their base or root form. So words like traveling, traveled, and traveler all become travel. This helps the model recognize that these words are related, which improves accuracy in tasks like sentiment analysis or topic detection. An important step is filtering out stop words, common words like the, is, or at, that don't carry much useful information. Removing these words helps the model focus on the meaningful parts of the text that tell us what the guest really thinks. Sometimes we use parts of speech tagging, which labels each word with its grammatical role, whether it's a noun, verb, adjective, and so forth. This gives more nuanced information about the structure and meaning of the sentences, which can be useful in advanced NLP tasks like named entity recognition. Once the text is cleaned and normalized, we need to convert it into numbers because machine learning models work with numerical data. One common method is creating a document term matrix where each document, like a review, is represented by the frequency of each word it contains. This is often called the bag of words model since it counts words without considering their order. Building on that, we use TF-IDF, or term frequency inverse document frequency, which is a smart extension of the bag of words. Instead of just counting words, TF-IDF weighs each word by how important it is, giving more emphasis to words that are frequent in one document but rare across all documents. This helps the model focus on words that truly distinguish one review from another, improving classification and clustering performance. By carefully following these pre-processing steps, cleaning, normalizing, tokenizing, and vectorizing, you transform messy travel reviews or messages into a structured format. This clean, numerical representation forms the solid foundation for any machine learning or deep learning model you build next, whether it's predicting customer sentiment or summarizing trip feedback. Let's carefully walk through this text pre-processing pipeline tailored for travel reviews using pandas and NLTK. We start with a sample data set of hotel reviews, each with a rating, price, and raw review text. Notice the text contains uppercase letters, punctuation marks, and even an emoji in one of the reviews. Our goal is to transform these raw reviews into a clean and structured form for machine learning. Step 1. Lowercase conversion period. The first transformation converts all text to lowercase. This simple standardization step ensures that words like hotel, hotel, and hotel are all treated the same. Without this, the model might mistakenly think they are different words, increasing the complexity unnecessarily. In the output, you can see the new column cleaned to review where every letter is lowercase, like great location, very clean, instead of great location, very clean. Step 2. Noise removal. Next, we remove punctuation and special characters using regular expressions. This means that exclamation points, commas, and emojis, like the smiley face, are stripped out, leaving only letters and white space. This step is essential because punctuation often does not add value for text classification or clustering models. In the processed output, the clean review column now contains text free of these symbols. For example, great location, very clean, without commas or exclamation points. Step 3. Tokenization. Then we tokenize the clean text, breaking each review sentence into individual words or tokens. This converts a string into a list of words. For instance, the sentence, great location, very clean, becomes great location, very clean. This breakdown makes it easier to analyze the frequency and meaning of individual words rather than the entire sentence as a whole. Step 4. Stop word removal. We then remove stop words, which are common but usually uninformative words like the, was, and, or very. Removing these helps the model focus on the key descriptive words. In the output column tokens no stop, you can see the token list is now shorter and more meaningful. For example, great, location, clean without every. Step 5. Lemmatization. Finally, we apply lemmatization to reduce words to their root forms. For example, staying, stayed, and stay all become stay. This normalization reduces the vocabulary size and groups related word forms, improving model efficiency and accuracy. In the lemmatized column, tokens like hotel, bomb, or worth price represent these root words ready for analysis. Optional step, part of speech tagging. While not shown in this exact code snippet, POS tagging assigns grammatical roles to words such as nouns, verbs, or adjectives, which can further enhance model understanding, especially for complex NLP tasks. In this updated version of the code, we use pandas' built-in str replace method with regular expressions to clean the text. This approach is more concise because it allows us to apply powerful pattern matching and replacement directly on the entire column in just a couple of lines without needing to define a separate function. Because pandas operations like str replace are vectorized, they process all rows in the data frame at once, which is typically faster and more efficient than applying a Python function row by row. This not only makes the code cleaner and easier to read, but also improves performance, especially when working with large datasets. In contrast, the earlier version used a custom function with re.sub applied to each row via .apply. While this works fine, it is more verbose and can be slower because it calls a Python function for each individual review instead of leveraging pandas' optimized string operations. So, using pandas' vectorized string methods with regex helps us write cleaner, more maintainable code that runs faster, both important factors when pre-processing large amounts of text data in real-world NLP projects. We begin by importing the key Python libraries. Pandas is used to store our reviews in a structured table-like format. The re and unicoded data libraries give us tools for cleaning raw strings, handling punctuation, and normalizing messy Unicode characters like accents and emojis. From the NLTK toolkit, we load stopwords, WordNet, and the WordNet lemmatizer, which are essential for filtering and reducing words to their base form. Next, we prepare the necessary NLTK resources. These downloads are like dictionaries and models that NLTK needs to tokenize text, recognize stopwords, lemmatize, and assign parts of speech. For example, Punkt allows NLTK to split text into sentences and words, while stopwords provides a curated list of common filler words such as the or is. The WordNet resource supports lemmatization, ensuring words like running and ran are reduced to the root run. Finally, the average perceptron tagger provides part of speech tagging, labeling each token as a noun, verb, adjective, and so forth. Our sample dataset is a miniature version of what a travel company might collect. Each row contains 3 types of data: a numeric rating, the price of a booking, and a written review. This mix illustrates why pre-processing is important. Numbers are straightforward for computers, but the free text reviews are messy, subjective, and full of variations. For instance, a review like "This hotel was the bomb" combines slang, punctuation, and even an emoji, all of which need to be normalized before analysis. We also add a configuration toggle to decide whether or not digits should be removed from reviews. This is a practical design choice. In some applications, numbers like room 305 or open 24/7 provide meaningful information. In others, numbers can act as noise. By keeping this step optional, the pipeline remains flexible for different business contexts. To handle messy text, we define a few helper functions. The Unicode normalization function ensures that all characters are consistent, by decomposing them into base characters, stripping away accents, and recomposing them into a uniform format. This guarantees that words like cafe and cafe are treated the same. Another helper function handles contraction expansion. Human language is full of shortcuts like it's or I'm, but for modeling, it's better to expand these to it is and I am. This reduces vocabulary size and keeps the meaning clear. Finally, we also set up functions for mapping part of speech tags into WordNet categories and a small illustrative normalizer that strips off common suffixes like -ing or -ed. While basic, these functions demonstrate how we can standardize words further to capture their root meaning. Through this setup, we're equipping our pipeline to tackle every stage of text cleaning and normalization, from Unicode normalization and contraction handling, the removal of punctuation, stop word filtering, lemmatization, and part of speech tagging. Each of these steps transforms chaotic raw reviews into structured, machine-readable data that can fuel tasks like sentiment analysis, clustering, or automated travel recommendations. The first step in our pipeline is Unicode normalization and lowercasing. Raw text often contains accented characters, emojis, and formatting inconsistencies. For example, the word cafe and cafe should be treated as the same. By applying Unicode normalization, we break down characters into their base form, strip away unnecessary accents, and then fold them back into a standardized format. After that, we convert everything to lowercase. This ensures that words like hotel, capitalized first letter, normal word, hotel, all lowercase, and hotel, all caps, are considered identical during analysis, avoiding artificial duplication in our vocabulary. The second step is contraction expansion. Human language is filled with shortcuts. Think of phrases like it's, don't, or I'm. While convenient for writing, contractions increase the number of unique tokens in the dataset. Expanding don't to do not and I'm to I am reduces this variation and makes it easier for downstream models to capture meaning. In practice, this is done using regular expressions that replace contracted forms with their expanded equivalents. The third step focuses on removing punctuation and symbols. Reviews often include exclamation marks, question marks, emojis, or decorative characters. For example, the hotel was amazing. Contains symbols that don't add much analytical value. By stripping these characters with a regex replacement, we simplify the text without losing its meaning. This step also improves tokenization later by ensuring that we only split meaningful words. In the fourth step, we optionally remove digits. Numbers can either be useful or distracting depending on context. In some reviews, a number like room 101 might matter, while in others, 24/7 is just noise. Our pipeline makes this configurable by default, removing all numeric digits to keep the text clean. Next, we apply whitespace normalization in step 5. After all the replacements above, reviews might contain multiple consecutive spaces. By collapsing these into a single space and trimming edges, we ensure that the text is tidy and uniform. This makes tokenization more reliable and avoids generating empty or meaningless tokens. Step 6 introduces tokenization. Here, each review is broken down into individual words or tokens. For instance, great location, very clean becomes great location, very clean. Tokenization transforms continuous text into discrete units that we can analyze or model further. The seventh step is stop word removal. Stop words are common words like the, was, or and that don't carry much meaning. Removing them helps focus the analysis on the words that matter most, such as location, clean, or price. This reduces noise and improves both efficiency and model interpretability. In the eighth step, we add part of speech tagging. Each token is labeled with its grammatical role, noun, verb, adjective, and so on. For example, loved would be tagged as a verb, while hotel would be tagged as a noun. This linguistic information can enrich models by distinguishing how words function in context, making tasks like sentiment analysis more precise. The ninth step applies lemmatization with part-of-speech guidance. Unlike simple stemming, lemmatization reduces words to their base dictionary form while respecting their grammatical role. For instance, better becomes good as an adjective, while running becomes run as a verb. Using POS tags ensures that words are lemmatized accurately instead of mechanically chopping off suffixes. This produces cleaner, more semantically meaningful tokens. Finally, the 10th step creates convenience columns to make analysis easier. We rejoin filtered tokens into cleaned text for quick viewing, and we apply a small naive normalizer to strip off common suffixes as an illustrative step. These columns provide both human-readable and machine-friendly versions of the processed reviews, making it simple to compare raw text with its cleaned and normalized counterpart. We began our journey with a simple question: what is natural language processing, or NLP? At its heart, NLP is the bridge that allows computers to work with human language. The reviews we write, the questions we ask, even the casual expressions we use in everyday life. From the start, we saw how easy it is for humans to understand a review, like the hotel was clean and close to the city center, while for a computer, it's nothing more than a string of characters. That's where NLP comes in, transforming those characters into meaningful insights. From there, we explored the wide range of NLP applications and techniques. We looked at traditional approaches like TF-IDF and naive Bayes, which paved the way for early breakthroughs in text classification and clustering. We then moved into more advanced methods such as recurrent neural networks and LSTMs, which added the ability to capture sequences and dependencies in language. And finally, we arrived at transformers, the architecture behind modern large language models like BERT and GPT, which allow machines to understand context, semantics, and even generate human-like text. We also connected NLP back to the broader data science workflow, showing how NLP projects fit seamlessly into the same pipeline as any other data-driven task. The only key difference is the extra pre-processing step, where raw text must be carefully cleaned and normalized before it can be modeled. This led us to dive deep into the pre-processing pipeline itself, step by step, converting text to lowercase, expanding contractions, removing punctuation and digits, normalizing Unicode characters, tokenizing sentences into words, removing stop words, applying lemmatization, and even adding part-of-speech tags for richer context. By the end, we transformed messy, inconsistent text reviews into clean, structured tokens that are ready for machine learning. So, from understanding the big picture of NLP to breaking down the nuts and bolts of pre-processing, we've laid a strong foundation for everything that follows. These are the building blocks of real-world NLP applications, from chatbots and recommendation systems to sentiment analysis and intelligent search. This concludes the first part of our tutorial series. If you found this journey helpful, make sure to like the video, subscribe to the channel, and turn on notifications so you don't miss the next lessons. Thanks for learning with us, and I can't wait to see you in the next part of the series. In this lesson, we're building a practical text pre-processing pipeline with spaCy. By the end, you'll see how tokenization, lemmatization, part-of-speech tagging, sentence segmentation, noun chunking, and named entity recognition all come together. We'll also add rule-based extraction with spaCy's matcher, and finish by injecting our own business knowledge using an EntityRuler. Everything runs on a small, realistic dataset of travel and hostel requests, so you can clearly see what each step produces. We start by setting up spaCy and a few helpers. If this is your first run, you'd normally install the libraries and download a language model, spaCy, pandas, and an _core_web_sm. In the code, we import spaCy, pandas, which we'll use to hold our small dataset, the matcher, spaCy's rule-based pattern engine, and span, a data type for contiguous pieces of text. The key line is NLP equals spaCy.load, open parenthesis, en_core_web_sm close parenthesis. This loads a ready-made English pipeline with several components, a tokenizer that splits text into tokens, a tagger that assigns each token a part of speech like noun or verb, a parser that figures out syntactic relationships and enables noun chunks, a lematizer that reduces words to base forms, and named entity recognition, NER, that spots things like money, date, and GPE, cities, countries. The SM model is small and fast, perfect for tutorials. If you later need word vectors for similarity, swap to n_core_web_md. Next, we create a tiny realistic dataset in a pandas data frame. Each row has an ID and a text string. The examples intentionally include currency amounts, dates, cities, neighborhoods, and room types, because these give spaCy's built-in tools something meaningful to detect. For instance, I'm selling lemons for $5 today lets us see money and date in action while book a private room. Budget under 8,000 yen per night exercises both NER, money, and our own rules for prices and room types. Using a compact dataset is a great way to prototype. It runs fast, you can read the outputs easily, and the same code will scale to larger corpora later. Before we write the main analyzer, we add a rule-based layer with the matcher. Rules are helpful when you know the exact patterns you care about and don't need to train a model. We initialize the matcher with matcher open parenthesis nlp.vocab close parenthesis, which connects it to the same vocabulary as our pipeline. A pattern in spaCy is a list of token specifications, where each specification is a small dictionary that describes a single token. For example, lower, private, matches the word private in a case-insensitive way. Orth matches the exact $sign, and like enum. True matches tokens that look like numbers, including things like 60,000. Our price patterns cover several forms. Number followed by currency words like JPY or yen, currency symbol followed by a number like $40, and even phrases like under $40 or below 8,000 yen. We also add a simple nights pattern, number plus night nights, and a few room type patterns, private room, dorm bedroom, capsule hotel. Finally, we register them with matcher.add open parenthesis, price close parenthesis, comma, price underscore pattern, matcher.add open parenthesis, nights close parenthesis, and matcher.add open parenthesis, room type close parenthesis. From now on, whenever we run the matcher on a document, it will return spans that match these labels. The heart of the notebook is the analyze request text function. You'll hear me say doc a lot. Doc equals NLP open parenthesis text. Close parenthesis is where spaCy processes the string through the pipeline, and the resulting doc object holds tokens, sentences, entities, and more. We extract several basics in one go using list comprehensions. Tokens collects the original text of each token. Lemmas collects base forms, e.g. running, run. Stop word flags is a sequence of booleans marking common stop words like the and. And pastas tags pairs each token with its universal part of speech label. We format them as token/POS strings for readability. These lists give you a token level view that's immediately useful for cleaning and feature engineering. We also pull out sentence segmentation with s.text for s in doc.sense. This splits the input into sentences, which is handy for tasks like summarization, QA, or just formatting results cleanly. Using the parser, we gather noun chunks with chunk.text for chunk in doc.noun chunks. Noun chunks are short, self-contained phrases like a private room or a capsule hotel. They're powerful because they give you subject/object phrases without writing complex dependency code yourself. Next, we collect named entities as strings like Tokyo GPE or 8000 JPY money, which makes it easy to inspect what the NER has recognized. After the statistical passes, we add rule-based matches by calling matcher.doc. This returns a list of matches. Each match has a label ID and start/end token positions. We translate the ID back to a string label, for example price, and extract the text span. We store matched spans in 3 lists: prices, nights, and room types. This hybrid approach, statistics plus rules, gives you flexibility. NER will catch many standard patterns, but your rules can guarantee coverage for business-specific phrasing like under $40 that you don't want to miss. To make the output more actionable, we compute a few lightweight intent flags. We scan the document for booking verbs, words like book or reserve, and if found, we set a booking intent flag. Similarly, if the user asks to recommend, we set recommendation intent. Finally, if we see the lemma budget or we detected any price, we set a budget constraint flag. These are simple keyword checks using token attributes like token, lower underscore, and token lemma underscore, but they're often enough to bootstrap a working intent layer before you build a trained classifier. Before returning, we deduplicate the list with listdict.fromKeys. This is a common Python trick to remove duplicates while preserving the original order. The function then returns a clean dictionary containing the original text, sentences, token level info, entities, rule matches, and intent flags. The result is an easily serializable, analysis-ready structure you can log, test, and turn into features downstream. With our analyzer ready, we apply it to the whole dataset using pandas. dfText apply analyze request runs the function for each row and produces a series of dictionaries. We convert those dictionaries into a data frame via pd.dataframe open parenthesis results.tolist close parenthesis, and then join the original ID column so we can keep track of which row is which. For readability, we reorder the columns so they flow from raw input to structured output, ID and text, then sentences, token/lemma/stopword/pause features, followed by noun chunks, entities, our rule-based prices, nights, and room types, and finally, intent flags. We also increase pandas display width pd.set option display.max width 150 so longer text isn't truncated, and print the whole table with toString indexed false. This table acts like a debugging dashboard. Compare the NER entities column against your rule-based prices to see where each shines. Scan noun chunks to understand what the parser thinks are meaningful phrases, and glance at intent underscore flags to see whether a basic user intent is being detected. As an optional final step, we add an EntityRuler to inject domain knowledge directly into the pipeline. We create it with nlp.addPipe EntityRuler before NR. Placing it before the statistical NER means your rules can take precedence on conflicts. The patterns here are simple phrase patterns, dictionaries with label like destination, and pattern like Tokyo or La Rambla. After adding patterns, we run the pipeline on one of our sample texts and print the recognized entities. You should now see your custom destination labels whenever those city or neighborhood names appear. This demonstrates a powerful real-world strategy. Let the trained model handle general categories and use the ruler for business-critical terms. brands, product names, locations that you must identify reliably without retraining a model. That's the full pass through the notebook. You now have a practical pre-processing stack that covers token-level features, tokens, lemmas, stop words, POS, sentence and phrase structure, sentences and noun chunks, named entities from NER, precise rule-based extractions for patterns you care about, and a lightweight intent layer. Welcome back to BrainOmega. This is NLP tutorial number 3, and today we're going hands-on with one of the most important steps in natural language processing, vectorization. Our goal is simple but powerful. We want to take clean text and turn it into numbers so we can analyze it, compare documents, and eventually feed it into machine learning models. To do this, we'll build document term matrices. These are tables where each row represents a document, each column represents a word, and the values capture how strongly that word appears in the document. We'll explore two of the most common techniques. CountVectorizer, which gives us a basic bag of words representation by counting word frequencies. FitVectorizer, which goes a step further by weighting words according to their importance across the whole dataset. For context, we'll use a small travel-themed dataset with short reviews and booking-style messages, things like hostel recommendations, budget notes, and location mentions. By the end, you'll see exactly how raw text becomes structured data, ready for any downstream NLP task. We'll start by importing the essentials for this notebook. From pandas and NumPy, we get clean table handling and basic array utilities. From scikit-learn's feature extraction.txt, we bring in CountVectorizer and TF-Vectorizer, the two workhorses we'll use to convert text into numbers. We also import Cosine Similarity, which lets us measure how similar two documents are once they're vectorized. Next, we define a tiny travel-themed dataset of short messages, things you might see in a hostel or travel agency context, mentions of neighborhoods like Shibuya or Asakusa, budgets in JPY or USD, trip dates, and room types like dorm, private, or capsule. These snippets are already lightly cleaned for the demo. Lowercase, minimal punctuation, and numbers kept where they matter like prices and dates. Finally, we load everything into a data frame with a doc ID column and a text column. This makes it easy to index documents, join results later, and feed the text series directly into our vectorizers. With imports ready and a small realistic data set in place, we're set to build document term matrices and compare documents by their content. Before we can use machine learning on text, we have to turn words into numbers. That's what vectorization does. We'll look at two classic approaches you'll see everywhere. Counts, bag of words, just how many times each term appears in a document. TF-IDF, not just frequency, but also how informative a term is, boosting rare, useful words and downweighting very common ones. To start, we build a bag of words with scikit-learn's CountVectorizer. Calling fit_transform on our text column does two things at once. Learns the vocabulary from all documents, the set of unique terms it sees, and creates a sparse matrix where rows are documents and columns are terms filled with term counts. For readability, we convert that matrix into a pandas data frame. We use getFeatureNamesOut as column names the learned vocabulary and use docID as the index. Calling .head shows the first few rows so you can inspect which words appear in which documents and how often. Tip: later, you can customize CountVectorizer with options like stop words, minimum document frequency, or n-gram range equals 1 to 2 to ignore very rare terms, or include bigrams like Golden Week. Now let's zoom in on a single document to see what the bag of words actually captured. We pick a row ID, here it's 1, but you can change that number to explore other messages. We grab that row from counts_df, sort the term counts in descending order, and display only the terms with counts greater than 0. What you'll see is a compact list of the words that appear in this document and how many times each one shows up. This is a great sanity check. Do the top terms match the message's meaning? For example, a booking note might surface words like hostel, asakusa, budget, or night. A couple of tips. If you see lots of low-value words like the, and, consider adding stop words to the vectorizer. If important phrases get split, for example, golden week, try bigrams with n-gram range equals 1 to 2. Remember that each row is sparse. Most terms are 0 for most documents, so focusing on the non-zero terms is the quickest way to understand what stands out in a given message. Counts tell us what appears, but not what's important. That's where TF-IDF comes in. It boosts words that are frequent within a document, term frequency, but rare across the whole corpus, inverse document frequency. Common words that show up everywhere get down-weighted. Distinctive words that signal meaning get up-weighted. We use scikit-learn's tfida vectorizer just like CountVectorizer. Fit transform learns the vocabulary and builds a document term matrix, but now the values are weights instead of raw counts. By default, scikit-learn also L2 normalizes each row, so every document vector has unit length. This makes Cosine similarity comparisons more meaningful. For readability, we convert the sparse matrix to a pandas data frame with get feature names out as the columns and doc ID as the index, then show dot head. You'll notice values between 0 and 1, typically small decimals. Higher numbers mean a term is more characteristic of that document relative to the others. Now let's compare how the same document looks under two lenses, raw counts and TF-IDF weights. We pick a row ID, here it's 1, gather all non-zero terms for that document from each matrix, and sort them from highest to lowest. The counts view tells you which words appear most often in that message. Great for a quick snapshot of frequency. The TF-IDF view, on the other hand, highlights which words are most distinctive for this document compared to the rest of the corpus. What should you expect to see? Words that are specific to this message, like a location, asakusa, a room type, hostel or private, or a budget hint, JPY, night, often rise to the top in TF-IDF, even if they only occur once, because they don't appear in many other documents. Meanwhile, words that are common across the dataset, like room, budget, or under, can dominate counts but get down-weighted in TF-IDF. This side-by-side is a great sanity check. Counts explain presence, TF-IDF explains importance. If you're building features for a model, TF-IDF often gives better signal by focusing on what makes each document unique. TF-IDF gets even more powerful when you add a few practical options. Here we use 3 that you'll reach for all the time. Stop words equals English. Drops very common words like the and that rarely help models. MinDF equals 2. Ignores ultra-rare terms that appear in fewer than 2 documents. This reduces noise and keeps the vocabulary compact. Ngram range equals open parenthesis, 1, 2, close parenthesis includes both unigrams, single words, and bigrams 2-word phrases, so you can capture short expressions like golden week, private room, or near station that carry more meaning than the words alone. We fit this configured vectorizer on our text and convert the result to a data frame so you can inspect it easily. You'll notice the vocabulary now contains cleaner, more informative features, fewer throwaway words, and more useful phrases. This kind of tuning often boosts downstream performance and makes similarity searches more meaningful, especially in domain-specific corpora like our travel hostel messages. Once our documents are turned into TF-IDF vectors, we can measure how similar any two messages are by comparing their vectors. A popular choice is cosine similarity. It looks at the angle between two vectors rather than their length, which works well for text where overall length varies. Values range from 1.0, identical direction, down to 0, no similarity, and can go negative if vectors point in opposite directions. We compute a full similarity matrix with cosine similarity x TF-IDF. The result is a square table where rows and columns are documents, and each cell ij is the similarity between doc I and doc j. The diagonal is always 1.0 because each document is perfectly similar to itself. To make this more useful, we wrap the matrix in a pandas data frame indexed by docid, then create a small helper top match. For each document similarity row, we drop the self-entry, sort the remaining scores from highest to lowest, and return the top k matches, by default, the single best match. Applying this function across all rows gives you a quick nearest neighbor lookup. For every message, which other message is most similar in meaning and vocabulary. This is the foundation for practical features like deduplication, find near duplicates, recommendations, show messages similar to a query, and semantic search, retrieve the closest notes to a user's input. If your results feel too sensitive to common phrases, revisit your vectorizer settings, use stop words, raise min df, or include bigrams to capture key phrases like golden week or near station. There's one big limitation with bag of words methods like counts and tf-idf. They ignore word order. To see this, we build a tiny toy corpus with 3 sentences. I am happy, I am not happy, and I am very happy. We run both CountVectorizer and tf-Vectorizer and turn the results into data frames so we can read them easily. Look closely at the outputs. Both representations treat the document as just a bag of tokens. The phrases happy and not happy end up looking very similar because they contain the same individual words, even though their meanings are opposite. Likewise, very happy gets split into very and happy, losing the fact that those 2 words came together. This is the trade-off with simple vectorizers. They're fast, interpretable, and effective for many tasks, but they can't capture negation, multi-word expressions, or word order. If that matters for your problem, you have a few options. Include n-grams. For example, n-gram range equals 1, 2, so bigrams like not happy show up as their own features. Move to contextual embeddings, for example, BERT, that model word order and meaning in context. Use rules or simple preprocessing to catch common negations or phrases. This tiny example is a great sanity check. When results look off, ask whether your features are seeing the structure that carries the meaning. One simple way to add a bit of word order back into bag of words is to include bigrams, pairs of consecutive words. Here we set n-gram range, so the vectorizer creates features for both unigrams, single words, and bigrams, 2-word phrases. When we fit this on the toy corpus, we can now see a dedicated feature for not happy. In the resulting data frame, look at the 3 columns side by side, happy, not, and not happy. The sentence, I am not happy, has a count for not happy, clearly signaling the negation. The positive sentences, I am happy and I am very happy, don't trigger that bigram, so they remain distinct. This doesn't solve all ordering issues, but it partially fixes important cases like negation and short phrases as a rule of thumb. Use bigrams or even trigrams when key meaning lives in short phrases, not happy, near station, golden week. Keep an eye on vocabulary size. N-grams grow features quickly. If needed, restrict with minDF, max features, or domain-specific stop words to keep things manageable. Sometimes you'll want to take your document term matrices outside of Python, for example, to use them in another machine learning tool, plug them into a BI dashboard, or simply inspect them in Excel. That's where exporting to CSV files comes in handy. Here, we save 3 different versions: the raw counts matrix, the basic TF-IDF matrix, and the tuned TF-IDF with stop words, min frequency, and bigrams. Each one becomes a standard CSV file that you can open, share, or feed into other workflows. The print statement confirms the file names so you know exactly what got saved. This makes your pre-processing pipeline more flexible. You can run the vectorization once in Python and then reuse the numeric features wherever you need them. Here are the big ideas to remember. CountVectorizer turns text into a simple document term matrix of word counts, a classic bag of words view. VADER goes further by reweighting terms by importance, so rare but informative words get higher scores and common filler words matter less. Because bag of words ignores word order, it can miss meaning. For example, not happy versus happy. Adding n-grams, like bigrams, helps capture short phrases, while modern embeddings, for example BERT, capture context best when you need deeper semantics. Welcome back to BrainOmega. This is NLP tutorial part 4, and today we're building a practical sentiment analysis pipeline tailored to travel and hostel text. Short reviews, booking style chats, and social posts. We'll focus on VADER, the valence-aware dictionary and sentiment reasoner, because it works directly on raw text where punctuation, casing, emojis, and even exclamation marks matter. That makes it a perfect fit for informal travel content. In this session, you'll learn how to score individual sentences and full datasets, then convert those scores into positive, neutral, negative labels using sensible thresholds. We'll roll up results by property, hostel, and by channel, booking, hostel site, X or Twitter, and build quick visualizations to understand sentiment distributions and property-level KPIs at a glance. Along the way, we'll call out how VADER handles negation, not great, emojis, happy face, angry face, and domain terms common in travel. By the end, you'll have a reusable end-to-end sentiment workflow. Load real-world text, score it with VADER, label it cleanly, aggregate and visualize trends, and generate insights you can act on, whether that's improving guest experience, monitoring channels, or tracking reputation across properties. First, we'll install the dependencies we need for this notebook. The command pip install VADER sentiment pandas, matplotlib pulls in VADER for sentiment scoring, pandas for data handling, and matplotlib for quick charts. In Colab, the leading exclamation mark runs this as a shell command. Locally, you'd run the same pip install in your terminal. After that, we import the libraries, pandas for data frames, matplotlib.pyplot for plotting, and sentiment intensity analyzer from VADER, which is the tool that actually computes sentiment scores. We also set a small pandas display option so long text, like full reviews or social posts, doesn't get truncated in the notebook. When you see setup complete, it just means everything is installed and imported, and we're ready to start analyzing sentiment. We'll kick things off with a small, realistic data set that looks like what you'd actually collect from booking sites and social platforms. Each row is one text entry with 4 columns. Date in YYYY-MM-DD format, property name, the hostel, channel, where the text came from, hostel world, Google reviews, Instagram, X/Twitter, etc., and text, the raw message we'll analyze. Notice we're keeping emojis, punctuation, and casing. That's intentional. VADER reads those signals, exclamation marks, all caps words, not, plus adjective, emojis like face with smiling eyes or face with angry eyes. They all nudge the sentiment score in meaningful ways. This starter dataset gives us a bit of variety. Clear positives, rooftop vibes, friendly staff, mixed feedback, great location but noisy AC, strong hype posts, all caps plus fire emojis, service issues, late check-in, cold showers, and value comments, clean kitchen, comfy beds, nice views. It's perfect for demonstrating how a rules-based model reacts to tone, emphasis, and negation across different channels and properties. In practice, you can swap this out for your own CSV. Just make sure you preserve raw text and keep a date and property column so we can aggregate by time and by hostel later. Pro tip, parse date as a date-time type for easy grouping, and keep the channel column so you can compare patterns across booking versus Google versus social. With this data frame in place, we're ready to score sentiment and turn these messages into actionable KPIs. Before we score a whole dataset, let's understand what VADER returns. For any piece of text, VADER gives a small dictionary with 4 keys: neg, nu, and pos, which are the proportions of negative, neutral, and positive signal it detected, and compound, a single overall score between -1 and +1. In practice, compound is the one to watch. It combines everything, including punctuation, all caps, emojis, and negations, into one sentiment number. The VADER authors suggest simple, sensible thresholds for labeling. Compound greater than or equal to 0.05, positive. Compound less than or equal to negative 0.05, negative. Otherwise, neutral. These work well out of the box, but you can tune them for your domain if you find the labels too strict or too loose. In the code, we create an analyzer with sentiment intensity analyzer, grab a sample text from our data frame, and call polarity scores sample. That returns the 4-key dict described above. Printing the original text alongside the scores is a great sanity check. You'll quickly see how exclamation marks, words like not, and emojis shift the compound score up or down. To make the notebook reusable in real projects, we'll wrap VADER scoring and labeling in 2 small clean utilities. The first, getCompound, takes a raw text string and returns VADER's compound score from -1 to +1. We deliberately pass the raw text as is, no lowercasing or emoji stripping, because VADER uses punctuation, all caps, emojis, and negations to detect tone. The function accepts an optional underscore analyzer, so you can inject a shared analyzer, useful for testing or parallelization, and otherwise falls back to the global analyzer. The second helper, label from compound, turns that numeric score into a human-readable label using VADER's default thresholds. Scores greater than or equal to 0.05 map to positive. Scores less than or equal to negative 0.05 map to negative, and everything in between is neutral. These cutoffs are solid defaults, but treat them as knobs. Tighten them if you want fewer positives, negatives, more neutrals, or loosen them if you want stronger polarity calls. With these 2 functions, the rest of your pipeline becomes simple and readable. Compute a compound score per row, map it to a label, then group by property/date/channel for KPIs and charts. In production, you can vectorize this over a pandas series, dftext.apply getCompound, and cache the analyzer so scoring stays fast. Now let's run our helpers across the whole data frame. We take the text column and apply getCompound to compute VADER's overall sentiment score for each row. That becomes a new compound column with values between -1 and +1. Next, we map those scores to labels using label underscore from compound, creating a sentiment column with positive/neutral/negative. This keeps the numeric signal for analysis while giving you an easy, human-readable tag for dashboards and filters. At this point, you can quickly sanity check a few rows to see if the labels match your intuition. For example, emojis and exclamation marks pushing reviews positive, not, plus complaint pushing them negative. Pro tip, if you plan time-based charts later, convert date to a date time, PD dot to underscore date time, so you can group by day/week/month and roll up sentiment trends by property and channel. With scores and labels in place, we can turn raw reviews into actionable KPIs. First, we group by property name and compute the average compound score for each hostel. This gives a quick, sortable leaderboard of overall sentiment. Higher means guests generally feel more positive about that property. Lower points to potential issues. Sorting in descending order surfaces your best performing hostels at the top, while those near the bottom may need attention. This single metric is great for dashboards and weekly reports. You can pair it with volume, number of reviews, to distinguish a truly strong signal from a small sample. Averages are useful, but sometimes you need more granular insight into sentiment. Here we group by both property name and sentiment, then count how many reviews fall into each category. Using dot size gives raw counts, and dot unstack fill value equals 0 pivots. The sentiment labels into their own columns, so you get one row per property with counts for positive, neutral, and negative. Resetting the index makes it a clean data frame you can inspect or export. This distribution is powerful for understanding the shape of feedback. For example, two hostels might have the same average score, but one could be mostly positive with a few negatives, while the other might be split evenly between love and complaints. This breakdown helps you see if sentiment is consistently strong, polarized, or drifting toward neutral. In practice, you can extend this to include channels too, so you can compare how a hostel performs on Google reviews versus social posts versus booking platforms. Just like we did for properties, we can roll up sentiment by channel to see where guests are happiest or most critical. Here we group by the channel column, compute the mean compound score for each source, and then sort the results in descending order. The output shows an average sentiment score per channel, giving you a quick snapshot of how different platforms compare. This is especially useful because tone often varies by channel. Booking sites may lean more neutral and factual, while social media posts tend to be more extreme, either very positive, hype, emojis, all caps, or strongly negative when people vent. Tracking channel averages helps you understand not just what people feel, but where they express it most strongly, which is key for prioritizing marketing and guest engagement efforts. Let's turn our channel KPIs into a quick visual. This bar chart plots each channel on the x-axis and its average VADER compound score on the y-axis, so you can instantly see which platforms skew more positive or negative. Rotating the X labels keeps things readable, and tight layout prevents overlaps. Read it like a leaderboard. Taller bars mean happier tone on that platform. Shorter or negative bars point to places where feedback tends to be more critical. This simple view helps you prioritize where to focus, celebrate the channels with strong sentiment, and investigate what's driving weaker scores on others. Now let's visualize property-level sentiment. Each bar represents a hostel, and the bar height is its average VADER compound score across all reviews. Higher bars mean guests generally feel more positive. Lower or negative bars suggest issues worth investigating. Rotating the labels keeps long property names readable, and tight layout prevents overlap. How to use this chart. Treat it like a scoreboard. Celebrate the top properties. What are they doing right? Staff, cleanliness, events. For properties near the bottom, drill into recent reviews to spot recurring themes. Check-in delays, noise, cold showers, etc. Pair this view with review counts to distinguish a strong trend from a small sample, and consider slicing by channel or time, for example, month over month, to catch shifts early. VADER isn't just counting positive and negative words, it reacts to how people write. This quick test runs a few travel-style sentences through the analyzer to show 3 important behaviors: negation, emojis, and emphasis. Phrases like didn't like flip the tone of what follows, so you'll see the compound score drop even if the adjective itself is positive. Emojis such as face with smiling eyes or face with tears of joy shift scores in the expected direction. Hype emojis like fire and exclamation marks add intensity, often pushing already positive lines further up. All caps words, for example, amazing, are treated as stronger emphasis too. You'll also notice VADER can handle mixed sentiments in one sentence. Amazing beds, but cold showers, by balancing the positive and negative parts. And a classic subtlety, not bad, usually lands slightly positive rather than neutral or negative. Printouts of polarity scores make this visible at a glance, so you can calibrate expectations and adjust labeling thresholds if needed. Pro tip, VADER does well on informal text but won't catch sarcasm reliably. For channels heavy on irony, review edge cases or complement with human checks. Ready to run this on your own reviews? All you need is a CSV with at least a text column, the raw messages you want to analyze. If you have them, include optional columns like date, property name, channel, and rating so you can group by time, roll up KPIs per hostel, compare platforms, or sanity check sentiment against stars. The tiny example shows the expected layout, 1 row per review, with the text kept as is, emojis, punctuation, and casing included, so VADER can pick up tone and emphasis. In Colab, upload your file, point pd.read_CSV to its path, and then apply our helpers. Compute the compound score for each row and map it to a sentiment label. A quick dot head lets you verify everything looks right before you move on to aggregations and charts. Pro tips: convert date with pd to datetime if you plan time series plots, and if your file isn't UTF-8, pass encoding equals, for example, UTF-8sig. That's it. Swap in your CSV and you've got a drop-in sentiment pipeline for your own travel data. Here are some practical tips to make this workflow production ready. First, keep the raw text for VADER. Don't strip emojis, punctuation, casing, or exclamation mark. Those cues carry real sentiment signal. Second, tune the label thresholds if your domain is skewed. For example, hospitality often leans positive. Tightening or loosening the cutoffs can reduce false positives/negatives. For longer reviews, score per sentence and aggregate, mean, median, or even max to capture standout emotions. Consider hybrid setups. Use VADER for fast, robust polarity and complement it with lightweight ML classifiers to detect domain themes like cleanliness, Wi-Fi, or check-in experience. Put the results on a time axis, weekly or monthly KPIs per property and channel, to spot declines early and act before they snowball. And always spot check a small sample, especially edge cases like sarcasm or mixed sentiment, so you can calibrate thresholds and set realistic expectations with stakeholders. Welcome to part 5 of our NLP series. In this session, we're diving into one of the most fundamental techniques in text analytics, text classification with naive Bayes. You'll learn how machines can automatically label text, from detecting spam emails to classifying travel reviews, using simple yet powerful probabilistic models. We'll explore both multinomial and Bernoulli naive Bayes, build full end-to-end pipelines in scikit-learn, and compare feature extraction strategies like bag of words and TF-IDF, even adding n-grams for richer context. By the end, you'll know how to train, evaluate, and interpret your own text classifiers, including tuning hyperparameters and inspecting which words drive your model's predictions. This tutorial bridges theory and practice, short, focused, and perfect for anyone ready to make their text data truly intelligent. Let's make sure your environment is ready before we touch any code. If you're running in Google Colab, this cell installs the exact packages we need for the tutorial. scikit-learn for modeling and matplotlib 3.x for plotting, so everything behaves predictably. If you're on a local Jupyter setup and already have scikit-learn installed, you can skip or comment out this cell. The goal is simple. Lock in the right dependencies up front so the rest of the notebook runs cleanly, without version surprises later. We'll start by pulling in everything we need for a clean end-to-end text classification workflow. NumPy and Matplotlib handle arrays and quick plots. From scikit-learn, we load the 20 newsgroups dataset utilities, 2 vectorizers, CountVectorizer and TFID-vectorizer to turn text into numbers, and the core training tools, train test split for proper evaluation, pipeline to stitch pre-processing and models together, and grid search CV for simple hyperparameter tuning. We bring in the 2 naive Bayes variants we'll compare, Multinomial NB and Bernoulli NB, as well as a dummy classifier to give us a baseline that answers, are we beating trivial? For reporting, we import accuracy, precision, recall, and F1, the classification report, and the confusion matrix so we can judge performance from multiple angles. A couple of small helpers, bunch for tidy dataset containers, text wrap for prettier printing, iter tools for small utilities, and warnings to silence noisy logs. Round things out. Finally, we fix a random seed for reproducibility, so your results match mine and small random differences don't distract from the lesson. Text classification is the task of assigning labels to raw text. Think email as spam versus ham, reviews as positive versus negative, or news articles by topic. The workflow is always the same. Turn text into numeric features, vectors, then train a model to map vectors to labels. A bag of words representation counts how often tokens appear, while TF-IDF keeps the information but downweights very common words, highlighting terms that are more distinctive. We start with simple, scalable models first. Naive Bayes is a classic baseline that's fast, easy to train, and often surprisingly strong on text because word counts align well with its assumptions. To keep training fast and lightweight, we'll use an 8-class subset of the 20 newsgroups corpus spanning computers, recreation, science, and politics. We load separate train and test splits with fetch 20 newsgroups, and we remove headers, footers, and quoted text so the model focuses on the content, not metadata or email boilerplate. From the fetch data, we pull xtrain, ytrain, xtest, ytest, and keep target names for readable class labels. This gives us a realistic multi-class problem with enough variety to showcase vectorization, naive Bayes variants, and evaluation without the heavy runtime of the full 20-class dataset. Before training, it's helpful to look at a few raw documents to see what the model will face. This cell prints 3 training samples along with their human-readable label from target names. We do a little formatting, strip leading, trailing whitespace, replace line breaks with spaces, and use textwrap.fill to wrap text to a readable width, so each snippet fits nicely in the notebook. Skimming these examples is a quick sanity check. You'll get a feel for vocabulary, length, and style across classes, for example, technical jargon versus sports lingo, and you may spot artifacts, signatures, boilerplate that can influence vectorization choices later. If a sample looks odd or mislabeled, it's a good reminder to keep evaluation honest and consider simple pre-processing tweaks only if they generalize. Before modeling, it's smart to check class balance. This cell counts how many training examples belong to each of the 8 categories and plots them as a bar chart. Skimming the distribution tells you whether the dataset is imbalanced. If some bars are much taller, a naive classifier could inflate accuracy by over-predicting those dominant classes. Knowing this up front helps you interpret results. For example, prefer macro average precision, recall, F1, consider stratified splits, already handled by the dataset, and, if needed, try simple fixes like class-weighted metrics, balanced baselines, or collecting more data for underrepresented topics. Start with a sanity check baseline so you know what doing nothing smart looks like. Here we build a simple pipeline that vectorizes the text with a basic CountVectorizer capped at 20,000 features just to bound size, and then uses a dummy classifier with the most frequent strategy, which means it always predicts the single most common class from the training set. We fit this on the training data and score it on the test set to get a baseline accuracy. If your real models can't beat this number, something's off: data leak, bad pre-processing, or a mislabeled split. If they only beat it by a hair, you'll know to revisit features, for example TF-IDF n-grams, or try a more suitable algorithm. This quick check keeps your expectations grounded and makes later improvements meaningful. Naive Bayes assumes that once you know the class, each feature behaves independently of the others. For text, that means, given a topic, the presence or count of each word is treated as independent evidence. It's a strong simplification, but in high-dimensional text, where most words are absent and a few are highly informative, it works surprisingly well. There are two classic flavors for NLP: Multinomial NB, which models token counts, how many times each word appears, and Bernoulli NB, which models binary presence, absence, did the word appear at least once. Both use a smoothing parameter called alpha, Laplace Lidstone smoothing, to avoid zero probabilities for words never seen with a class. Set it too low and you risk brittleness, too high and you over-smooth by flattening differences between classes. In the code, we build a scikit-learn pipeline that first turns text into bag-of-words features with CountVectorizer, up to 40,000 unigrams, then trains a multinomial NB classifier with alpha equals 1.0, a solid default. We fit on the training split and predict on the test split, then print overall accuracy and a classification report, precision, recall, and F1 per class. This gives you a strong, fast baseline for topic classification. If performance is close to your dummy baseline, try TF-IDF instead of raw counts, add n-grams, bigrams can capture short phrases, or tune alpha with a small grid search, for example 0.1, 0.5, 1.0, 2.0. A confusion matrix helps you see where the classifier succeeds and where it mixes classes up. Here we compute the matrix for the bag of words plus multinomial NB model and plot it as an image. Rows are true labels, columns are predicted labels. Ideally, you want most of the mass along the diagonal. That's where predictions match the ground truth. Off-diagonal cells reveal systematic confusions. For example, two computer categories or two sports topics getting mistaken for one another. Use this chart to guide improvements. Add bigrams to capture short phrases, switch to TF-IDF, or tune alpha if you see broad, low confidence bleed across several classes. Next, we upgrade the features and tune the smoothing. This pipeline replaces raw counts with a TF-IDF vectorizer that keeps up to 50,000 features, includes uni and bigrams in gram range 1, 2, and uses sublinear TF log scaling so extremely frequent terms don't dominate. On top we keep multinomial NB, but we let grid search CV pick the best alpha, Laplace or Lidstone smoothing by trying a small grid. 0.1, 0.5, 1.0, 2.0 with threefold cross-validation scored by accuracy. After fitting on the training split, we report the best params and CV score, extract the best estimator, and evaluate on the test set with accuracy and a full classification report. In practice, TF-IDF with bigrams plus a tuned alpha almost always beats plain BOW because it downweights boilerplate, captures short phrases, and sets just the right amount of smoothing to avoid zero probabilities without washing out class differences. Now let's try Bernoulli naive Bayes, which is built for binary features. It cares whether a term appears at least once, not how many times. We create a pipeline with CountVectorizer set to binary equals true and engram range equals 1 and 2. So we capture both single words and short phrases, hard drive, knee injury, etc. The classifier is Bernoulli NB, open parenthesis, alpha equals 0.5 close parenthesis, using a bit of smoothing to avoid zero probability pitfalls. After fitting on the training split, we predict on the test set and print accuracy, plus a full classification report, precision, recall, and F1 per class. Bernoulli NB can outperform multinomial NB when presence-absence is more informative than raw frequency, and when bigrams help disambiguate closely related topics. If results lag, try a small grid over alpha and consider pruning the vocabulary main df, max df to reduce noise. Time to peek inside the model and see which words drive its decisions. We refit a clean TF-IDF plus multinomial NB setup, using the tuned alpha from our grid if available. Then pull the learned log probabilities per class from clf.feature_log_prob_. Each row corresponds to a class and each column to a token, including bigrams, since we set n-gram range equals 1 to 2. By sorting these log probs within each class and taking the top n, we get a readable list of the most characteristic tokens for that label, the features the model considers strongest evidence. Read these lists like class fingerprints. For a computer hardware topic, you might see terms like SCSI, drive, or the bigram hard drive. For baseball, tokens like pitch, game, Yankees often float to the top. This is fantastic for error analysis. If you see off-topic or spammy tokens ranking highly, consider adjusting vectorization. For example, ManDF, MaxDF, domain stop words, or cleaning artifacts you chose to keep. It also highlights the value of bigrams. Phrases such as knee injury or graphics card carry far more signal than the unigrams alone. Keep in mind that TF-IDF already downweights ubiquitous words, so top tokens tend to be distinctive rather than merely frequent, exactly what you want when explaining why a naive Bayes classifier chose a class. Now let's look at where the model is getting things wrong. The helper inspect mistakes finds all indices where the true label and the predicted label don't match, and if there are any, it samples a few at random to print. For each mistake, we show the true class, the predicted class, and a nicely wrapped snippet of the original text for quick reading. This is the fastest way to do error analysis. You'll start to notice patterns, like overlapping vocabulary between two tech categories, sports jargon used in a medical context, or short, noisy posts that lack signal. Use what you learn to guide improvements. Add bigrams to capture phrases, tweak stop words or min-df or max-df, collect more examples for weak classes, or adjust alpha and vectorization choices. If you see no mistakes, celebrate. But usually a quick scan of these examples yields 2 or 3 actionable ideas for the next iteration. To wrap up, here are some practical ways to level up your text classifier. For noisy or misspelled data, social posts, support chats, try character n-grams. They capture subword patterns that survive typos and slang. Clean your feature space with stop word removal and sensible min-df or max-df thresholds to drop ultra-rare and overly common terms. If your classes are imbalanced, consider class weighting or balanced sampling, so minority categories aren't ignored. For deployment, keep your best scikit-learn pipeline intact and expose calibrated outputs. Use predict proba with thresholds and optional probability calibration to trade off precision versus recall per use case. Finally, benchmark against stronger linear baselines like a linear SVM, or logistic regression, SGD classifier, or logistic regression. They're still fast, often very competitive, and a great reference point for future improvements. Text classification is all about turning documents into vectors and then turning those vectors into decisions. Naive Bayes makes a bold but useful assumption that words are conditionally independent given the class, and in high-dimensional text, it works shockingly well. Remember that alpha is just smoothing. A smaller alpha leans harder on your data, while a larger alpha smooths more aggressively across classes. Always anchor your progress with a dumb baseline first, then prove your model is smarter, and don't stop at the metrics. Peek inside the model to see which words shout for each class. That's where the best error-fixing ideas come from. Welcome back to BrainOmega. This is NLP Tutorial Part 6, and we're diving into topic modeling, turning a pile of documents into a clean map of the main themes inside. We'll work in Google Colab for a smooth runtime and start by vectorizing text with count and TF-IDF, so our algorithms have something numerical to learn from. Then we'll compare three families of approaches: NMF, fast, interpretable, and excellent on small datasets with scikit-learn; LDA, a classic, probabilistic model that often shines on medium-sized corpora via Gensim; and modern embedding-based methods, BERTopic and Top2Vec, that leverage transformer embeddings to uncover richer topics at scale. You'll see when and why to pick each method. Start with NMF for compact datasets and quick, readable topics. Try LDA when your corpus grows and you want a Bayesian view of word-topic mixtures. And reach for BERTopic or Top2Vec when you've got more data, or you already use transformer embeddings and want nuanced, semantically coherent clusters. Along the way, we'll extract top words and example documents per topic, discuss labeling tips, and show practical knobs to tune topic quality. By the end, you'll have a clear hands-on workflow for discovering themes, whether you're exploring reviews, forums, or internal text collections, and a simple playbook to choose the right tool for your dataset size. Let's get the environment ready so every library you need for topic modeling is in place. This cell installs the core stack: scikit-learn, pandas, NumPy, matplotlib for data handling, pre-processing, and basic visuals. Next, it brings in classical topic modeling tools: Gensim for algorithms like LDA and PyLDA vispind for interactive topic visualization. For modern embedding-driven approaches, we install sentence transformers to generate transformer embeddings, UMapLearn for dimensionality reduction, and HDBSCAN for density-based clustering. Finally, we add two turnkey libraries, BERTopic and Top2Vec, that build topics directly from embeddings, plus a specific Gensim version for compatibility. These %pip commands work smoothly in Colab cells and ensure consistent versions. So once you see installs complete, you're set to vectorize text, run NMF, LDA, and try embedding-based topic models in one notebook. We'll start by loading a manageable text corpus so we can prototype quickly and compare topic models without long runtimes. Using scikit-learn's 20 newsgroups loader, we pull a small subset of 5 categories: space, graphics, baseball, Middle East politics, and medicine, and strip headers, quotes, footers, so our models learn from the content, not email metadata. We keep both the raw texts and their labels, then wrap them in a tidy data frame with 2 columns: text, the document body, and label, a human-readable class name. This gives us a realistic, multi-topic collection that's small enough for NMF and LDA to run fast, but rich enough to showcase differences across methods. If you'd rather use your own data, you can swap in a CSV with a single text column using the provided template later in the notebook. If you want to run topic modeling on your own data, this cell shows the quickest path in Colab. Use the file picker to upload a CSV, then read it with pd.read_CSV and make sure there's a text column. Every row should be one document: a review, post, paragraph, etc. We drop missing entries with dropna subset equals text and reset the index so downstream steps don't trip over gaps, then preview a few rows with head to sanity check the content. Keep pre-processing light at first. Remove only truly empty rows. Let the vectorizers or embedding models handle casing or punctuation later. For very large files, sample a few thousand rows while you iterate, then scale up once parameters look good. If your CSV has multiple text fields, combine them, for example, title plus body, into the text column before proceeding. With a clean DF text in place, you're ready to vectorize and run NMF, LDA, or embedding-based topic models. Before we feed documents into topic models, we'll do a light touch clean that keeps the words intact and the tutorial focused on modeling. The simple clean function normalizes whitespace, strips out bare URLs, they add noise but no topical meaning, and trims ends. No heavy lemmatization or stop word removal here because methods like NMF and LDA often benefit from seeing natural word forms and frequencies. We apply this to create a clean text column, then drop any rows that end up empty to avoid degenerate vectors. In a moment, we'll vectorize with both CountVectorizer and TFID-Vectorizer. As a rule of thumb, count is a common choice for LDA, which models counts probabilistically, while TF-IDF pairs nicely with NMF, which factorizes weighted features. This minimal preprocessing keeps your pipeline fast, interpretable, and easy to adapt to your own data later. Now we turn clean text into numeric features two ways, raw counts and TF-IDF weights, so our topic models have something to learn from. We configure both vectorizers with the same sensible knobs. Max features equals 20,000 to cap vocabulary size, ManDF equals 2 to drop ultra-rare terms, MaxDF equals 0.9 to ignore words that appear in almost every document, Ngram range equals 1 to 2 to include both unigrams and bigrams, helpful phrases like space shuttle or graphics card, and stop words equals English to remove high-frequency filler. CountVectorizer builds a document term matrix of counts, good default for LDA, while TF-IDF Vectorizer builds a weighted matrix that downweights ubiquitous terms, often a great fit for NMF. After fit transform, we get two sparse matrices, XCount and XTF-IDF, with the same shape, N documents, N features, printed at the end as a quick sanity check that our vocabulary size and corpus length look as expected. A quick rule of thumb before we pick a model, NMF tends to work best with TF-IDF features, while LDA is a probabilistic model that expects raw counts, bag of words. For small or medium-small corpora, NMF often produces clean, interpretable topics with minimal fuss. In this section, we use scikit-learn's NMF to decompose the TF-IDF matrix into two non-negative factors, W, the document topic matrix, and H, the topic term matrix. We set N components equals N topics to control how many topics we want. Seed with random state equals 42 for reproducibility. Use init equals N NDS VDA to get a good stable starting point and allow a few extra iterations. Max iter equals 400 so the factorization converges. After fitting, each row of W shows how strongly a document loads onto each topic, and each row of H, a topic vector, gives weights for terms in that topic. We then pull the top words per topic by sorting each row of H and printing the highest weight terms. This is your quick, human-readable summary of what each topic represents. If topics feel too broad, increase N topics. If they're fragmented, decrease it or tighten the vocabulary. For example, raise MindDF, add bigrams. To make your NMF topics tangible, it helps to read which documents load most strongly on a given topic. The helper TopDocs for topic takes the document topic matrix W, picks a topic ID, and sorts all documents by their score on that topic. It then returns the top N documents with their scores and a short snippet, first approximately 300 characters, for quick context. Printing these lets you sanity check the topic label you'd assign. Do the highest scoring docs really talk about the same theme as the top terms you saw in H? If not, you can adjust N topics, tighten the vocabulary, for example, MinDF, Bigrams, or try a different vectorizer. This doc level inspection is a fast way to refine topic names and spot mixed or noisy topics early. Here are a few quick tuning tips for NMF before we switch models. If topics look too broad or mixed, increase N components to get finer granularity. If they feel fragmented or repetitive, decrease it. Clean up the vocabulary by filtering very common terms with max DF and very rare terms with min DF, and experiment with n-grams. 1, 1 keeps only unigrams for crisp, distinct topics, while 1, 2 adds short phrases that can make topics more interpretable. Now let's try latent Dirichlet allocation LDA with Gensim, which is often a better fit for medium-sized corpora. LDA is a probabilistic model over raw counts, so we start from the CountVectorizer representation. To keep vocabularies aligned, we invert the scikit-learn vocabulary, InvaVocab, and reconstruct each document as a list of tokens present in that row of the sparse count matrix. We then build a Gensim dictionary from these token lists and convert each document to a bag of words using dictionary.doctubo. With the corpus and dictionary ready, we train ELDA model with a target number of topics, num topics equals 10 here, set a random state for reproducibility, and use modest passes and a larger chunk size for speed. Letting alpha equals auto and ETA equals auto helps LDA adapt topic or document sparsity and word distributions automatically. Finally, we print each topic's top terms to get a quick, human-readable summary. If topics look noisy, try tweaking the number of topics, raising min DF or lowering max DF to clean the vocabulary, or increasing passes for a bit more convergence. For a deeper, more intuitive look at your LDA results, this cell spins up an interactive Pyle-Davis panel right inside the notebook. Works great in Colab. The left plot, the intertopic distance map, shows topics as circles. Closer circles mean more similar topics, while larger circles indicate topics that cover more of the corpus. Click a circle to focus on one topic, and the right panel updates with a ranked bar chart of terms for that topic. The lambda slider lets you balance between raw frequency and distinctiveness. Lower lambda surfaces terms that distinguish the topic from others, while higher lambda leans toward the most frequent words. Use this view to name topics, spot overlaps, and decide whether to adjust number of topics, vocabulary filters, min DF or max DF, or passes. Note that Pyle-Davis can be memory hungry on large corpora. If rendering is slow, try sampling documents or limiting the vocabulary first. A few quick pointers before you run LDA at scale. More passes and iterations can stabilize topics, though they cost time. Start with 5 to 20 topics and adjust based on coherence and redundancy. And if you're modeling domain text, consider light lemmatization and a custom stop word list to reduce clutter. For larger or more varied corpora, switch to BERTopic, which builds topics from transformer embeddings, plus UMAP for dimensionality reduction, and HDBScan for clustering. Here we use a small fast sentence transformer, all mini LML6v2, to embed each document, then a UMAP instance with a fixed random state for reproducibility. In BERTopic, min topic size equals 10 merges tiny clusters into larger, more stable topics. Calculate probabilities equals true gives soft assignment scores, useful for ranking documents per topic, and verbose equals true prints progress so you can gauge runtime. If this cell feels slow on CPU, switch your Colab runtime to a GPU, T4 or similar, and rerun, the embedding step speeds up significantly. After fit transform, you get topics, the cluster ID per document with -1 for outliers, and probs, assignment confidences. Calling get topic info returns a tidy summary table with topic IDs, sizes, and representative words. Scan the top rows to spot dominant clusters and ensure the discovered themes match your intuition. From here, you can drill into any topic to see top terms and example documents, or tweak UMAP or HDBS scan settings and mine topic size to trade off granularity versus stability. Let's make the BERTopic results readable. The topic underscore info table lists topic IDs and sizes. We iterate over the first few and skip -1, which BERTopic reserves for outliers or noise that didn't fit any cluster. For each real topic, getTopic ID returns a list of term weight pairs, the most representative words, and their importance within that cluster. Read these like a topic label cheat sheet. The top 5 to 10 terms usually tell you exactly what the theme is. If a topic looks vague or mixed, you can increase mine topic size to merge small clusters, tweak UMAP parameters, for example nneighbors, min-dist, to change granularity, or adjust pre-processing, stop words, simple normalization. Once you're happy with the terms, jot down a short, human-readable topic name. You'll use that for dashboards and reports. To make your topics easier to read at a glance, BERTopic includes interactive plotly visuals. This cell renders a bar chart of the top terms per topic, for the first 10 topics by default. Each bar shows a term's importance within that topic, so you can quickly sanity check labels and compare themes side by side. The chart is interactive. Hover to see exact weights, click legends to filter, and zoom if needed. If Plotly isn't available in your environment or you're missing a front end, the try except will skip gracefully so your notebook keeps running. Use this view to confirm that the top words match your intuition. If topics look noisy, revisit pre-processing, tweak mine topic size, or adjust UMAP or HDBS CAN parameters for cleaner clusters. Top 2. Vec is another embedding-first approach that discovers topics without presetting K. It learns document embeddings, finds dense regions in that space, and names topics from the most representative words in each region. Because embeddings and clustering are learned jointly, it can surface coherent themes with minimal pre-processing, but it can be heavier than BERTopic depending on the embedder. In this demo, we keep things modest by slicing to approximately 1,500 documents and using the built-in doc2vec model with speed equals learn for a faster run. After training, getNumTopics tells you how many topics top2vec discovered, and getTopicsNumTopics returns the top words and their scores for each topic along with topic IDs. Printing the first few gives you an immediate sense of the clusters it found. If you want richer language understanding and have a GPU, try a stronger embedding model like use or distill use. If topics feel fragmented, reduce dataset size or switch speed settings. Evaluating topic models is part science, part judgment. There's no single accuracy number. A good approach is to mix automatic metrics with human sanity checks. Here we compute CV coherence with Gensim, which correlates reasonably well with how interpretable topics feel to humans. First, we convert our NMF output H into lists of top terms per topic. Next, we reuse the tokenized corpus, the same tokens we built from CountVectorizer, to create a Gensim dictionary and lightly trim extremes. Drop tokens that are too rare, no below, or too common, no above, to reduce noise. With topics, texts, and the dictionary in hand, coherence model, coherence equals C_V, gives a single score. Higher means the top words in each topic tend to appear together across documents. That means they cohere. Use this number to compare settings, for example, different N topics, vectorizers, or pre-processing choices, but don't rely on it alone. pair it with a diversity check. How many unique top words across all topics? And a quick human-in-the-loop pass where you read top terms and a few top documents per topic. In many real projects, the best model is the one whose topics are both coherent and useful downstream. For example, improving a classifier or making search facets more meaningful, even if it's not the absolute winner on a single metric. Finally, let's estimate topic diversity, a quick proxy for how much your topics cover different vocabulary. We take the top terms from each topic, count how many are unique across all topics, and divide by the total number of top terms. A score near 1.0 means topics use mostly distinct words, high diversity, while lower values suggest topics share many of the same terms, possible redundancy, or poorly separated themes. Use this alongside coherence. High coherence with very low diversity can mean you've discovered the same theme multiple times. High diversity with low coherence can mean topics are distinct but mushy. To improve diversity, try fewer topics, tighten the vocabulary, MindDF, MaxDF, stop words, or adjust n-grams. To improve coherence without tanking diversity, refine pre-processing or increase n topics slightly and recheck. Here's a simple path to run this notebook on your own corpus. Upload a CSV that has at least one text column, then follow Section 1, Option B, to load it, and Section 2 to do light cleaning and vectorization. From there, pick one modeling route, NMF, Section 3, LDA, Section 4, or an embedding-based method like BERTopic or Top2 VEC, Sections 5 to 6, and start with sensible defaults. Tune the key knobs for your choice, the number of topics, N components for NMF, num topics for LDA, vectorizer settings, MindDF, MaxDF, n-gram range, and for embedding approaches, UMAP or HDB scan, neighbors, mean dist, mean cluster size. When you've got a candidate, evaluate with Section 7, coherence plus diversity, skim the top words and a few top documents per topic, and iterate until the themes feel crisp and useful. A few practical gotchas to keep your results reliable. Pre-processing matters. Consider custom stop words, light lemmatization, and phrase detection, bigrams, to reduce noise without erasing meaning. Balance interpretability and coherence. Pick settings that produce topics you and stakeholders can name easily, not just the highest metric. For reproducibility, fix random seeds where possible and record library versions and parameters alongside your results. For performance, large corpora benefit from a GPU runtime and initially smaller embedding models. Scale up once your pipeline works. And finally, be thoughtful about ethics. Scan topic terms and example documents for bias, sensitive content, or privacy leaks before sharing outputs or deploying them. Welcome to the NLP Capstone project for the travel business. In this final project and NLP course, you're no longer just following a tutorial, you're playing the role of a data scientist at a company or business like travel. Think a hostel chain or a small travel agency drowning in guest reviews and messages. Your mission is to turn that unstructured text into clear, actionable insights the business can actually use. Across this notebook, you'll build an end-to-end NLP pipeline around customer reviews and booking style messages. You'll start by loading and exploring the data, then clean and normalize the text. The same way you learned in Part 1, you'll use spaCy to pull out structured information like destinations, nights, and locations. That means Part 2. Then vectorize the text with count and TF-IDF features. It is Part 3. On top of that, you'll layer VADER sentiment analysis that we explained in Part 4, train a naive Bayes text classifier for review sentiment, it refers to Part 5, and use NMF topic modeling, as discussed in Part 6, to uncover the main complaint and praise themes hiding in the reviews. At the end, you'll tie everything together into a simple insight function that can take a new incoming message and tell you its sentiment, category, and key entities in one go. You can stick with the toy dataset that's fully embedded in the notebook so everything runs out of the box, or you can swap in your own CSV of real reviews or messages and see how the pipeline behaves on data from your world. The goal isn't to chase perfect metrics, but to be able to answer real business questions like which cities or channels have the most negative sentiment. What are the main complaint topics by property or platform? When a new guest message arrives, what is it about? How does the guest feel? And which entities, city, hostel, and dates does it mention? One important caveat: the dataset here is small and synthetic, built for teaching rather than production. That means scores like accuracy, precision, recall, and F1 might bounce around and won't reflect state-of-the-art performance. That's okay. What matters in this capstone is that you understand the workflow, how cleaning feeds into vectorization, how sentiment and classification complement each other, how topic modeling adds context, and how all these pieces combine into a coherent, repeatable NLP system for a travel business. With more real data, you can retrain and tune this exact pipeline into something your stakeholders can trust in production. We'll kick off the project by getting your environment and sample data ready. The first cell is designed to be Colab friendly. If you're running in Google Colab, you can leave the %pip and Python-m spaCy download lines enabled to install everything you need. Pandas and NumPy for data handling, scikit-learn for vectorization, modeling, and metrics, NLTK and spaCy for classical NLP tools, and VADER for sentiment analysis. On a local machine where these are already installed, you can comment those lines out to avoid reinstalling. We also download a few NLTK resources: tokenizers, stopwords, WordNet, POS tagger, so lemmatization and POS-based cleaning later in the notebook work without errors. Next, we import the main libraries for the whole pipeline. Pandas and NumPy will hold and manipulate the review data. Matplotlib is there for quick plots. From NLTK, we get stopwords and the WordNet lemmatizer to normalize words. From spaCy, we load the small English model, which gives us tokenization, POS tags, and entities, plus tools like Matcher and EntityRuler to add custom patterns for travel-specific phrases. VADER's Sentiment Intensity Analyzer will score short, informal text like guest reviews and DMs. From scikit-learn, we bring in CountVectorizer and TF-IDF Vectorizer for turning text into features, train, test, split for building train test sets, Multinomial NB for our naive Bayes sentiment classifier, classification report, and confusion matrix for evaluation, and NMF for topic modeling. Finally, we create a small synthetic dataset of travel reviews and booking style messages stored as a list of dictionaries and turned into a data frame. Each row has the raw text, an optional numeric rating, 1 to 5 for reviews, none for unrated requests, the channel, booking, hostel world, email, Instagram DM, website chat, etc., and the city when known. The mix is intentional. We have positive, neutral, and negative reviews across Barcelona, Tokyo, Osaka, Kyoto, plus unrated inquiries like cheap private room or female-only dorms. This tiny corpus is enough to exercise every part of the pipeline: cleaning, entity extraction, sentiment, classification, and topics, while still being easy to inspect manually. Later, you can swap this out for a real CSV of your own reviews and messages without changing the structure of the notebook. Before we build any models, we need a quick feel for the data we're working with. This cell runs a mini EDA, exploratory data analysis, on our synthetic travel dataset. df.info shows us the overall shape, 31 rows with 4 columns, text, rating, channel, city, plus how many non-null values each column has. You'll notice that rating and city have a few missing entries. Those are our unrated booking or chat requests, which we'll treat differently from labeled reviews. We then print a handful of sample rows to see real examples of the text, their numeric rating, and which channel they came from. This is where you start to recognize the mix of glowing praise, complaints, and neutral comments across Barcelona, Tokyo, Osaka, and Kyoto. Next, we look at the ratings distribution with value counts, but only for rows that actually have a rating. This tells you how many 1-star, 2-star, 3-star, 4-star, and 5-star reviews you're dealing with, which later helps you define things like positive or negative thresholds and check for class imbalance in your classifier. Finally, we print the unique channels: Booking, Hostelworld, Google Reviews, Instagram DM, email, website chat, so you can see where feedback is coming from. Together, these few lines give you a quick X-ray of the dataset, how big it is, how labels are distributed, and what kinds of text you'll be processing before we start cleaning, vectorizing, and modeling. Now we turn our raw guest reviews into a clean, machine-friendly version while still keeping the original text around. The idea is to mirror what you learned in NLP Part 1. Raw text stays untouched for tools like VADER that care about emojis and punctuation, and a new column clean text holds a normalized version that's ideal for classical ML models, vectorizers, and topic modeling. We start by lowercasing everything so Wi-Fi and Wi-Fi are treated the same, then strip out URLs and HTML fragments that don't add semantic value. Next, we remove anything that isn't a letter or white space, which gets rid of stray symbols and numbers so we can focus on words. After that, we tokenize the text into individual words with NLTK, filter out stop words, common little words like the and very short tokens, and then run POS tagging so our lematizer knows whether a token is being used as a noun, verb, adjective, or adverb. With that POS information, the WordNet lematizer can map words to their base forms more accurately. Rooms to room, cleaning to clean, better to good where appropriate, so different inflections of the same word don't get split across features. The result is a clean text column where each review is reduced to a compact bag of meaningful tokens, like Amaze Location Barcelona Super Clean Room Friendly Staff, which you can see side by side with the raw text. This gives us the best of both worlds: expressive original reviews for rule-based tools and human reading, and normalized text for robust, data-hungry models. Next, we start turning messy guest sentences into structured fields using spaCy, just like in Part 2. The helper inspect doc takes a raw text string, runs it through the NLP pipeline, and prints three things: the original text, the list of detected entities, with labels like GPE for cities, time, or date for times, money, etc., and the noun chunks, short phrase-level groups like super clean rooms or friendly staff. Running this over the first few rows lets you see what spaCy picks up out of the box: city names such as Barcelona or Tokyo, time expressions like night, and meaningful noun phrases such as nice common area or rude receptionist. This is your starting point for extracting structured information like city, room type, and nights from free text. In the next steps, you'll extend this with a custom destination label and pattern matches so that a message like cheap private room in Osaka for 3 nights becomes clean fields the business can actually query. City equals Osaka, room type equals private room, nights equals 3. Now we upgrade spaCy from just recognize entities to extract the fields a travel business actually cares about. First, we add an EntityRuler to the pipeline before the built-in NER and feed it patterns for popular destinations like Barcelona, Tokyo, Osaka, Kyoto, Shibuya, and La Rambla. These get labeled as a custom destination entity, which gives us reliable city or area detection even if the default model misses them. Next, we define a matcher pattern for nights, a number followed by night or nights. So phrases like 3 nights or 2 nights are easy to pull out. For room types, we keep it simple. A small list of keywords such as dorm, dorm bed, and private room, and we just check for those substrings in the raw text. The extract structured info function runs a single review or message through this logic. It processes the text with spaCy, collects all named entities, and then picks the first destination-like entity, destination, GPE, or LOC, as the destination extracted. It uses the matcher to grab the number of nights, if we successfully parse a numeric value, and scans the lowercase text for any of the room type keywords. Finally, it returns everything as a series, so we can apply it to the entire data frame. After concatenating the results, you can see each original text alongside its extracted destination, extracted, nights extracted, and room type extracted. This is where raw sentences like cheap private room in Osaka for 3 nights turn into clean, queryable fields, exactly the kind of structure you need for dashboards, routing rules, or automated replies. Now that we have a clean text column, we can turn those words into numbers that models understand. This cell recaps the vectorization ideas from part 3 first. We create DF model, which filters out any rows where clean text is empty. Just a safety check so we don't feed blank strings to the vectorizers. Then we build a CountVectorizer with n-gram range equals 1 to 2, meaning it captures both single words and short phrases like dirty bathroom or friendly staff. Fit transform builds a vocabulary from all the tokens it sees and produces X counts, a sparse document term matrix where each entry is the count of that term in that document. We print its shape, documents times features, and a small sample of the vocabulary so you can see the kinds of tokens it's using. Next, we create a TF-IDF vectorizer with the same n-gram settings. Instead of raw counts, TF-IDF gives each term a weight based on how often it appears in a document and how rare it is across the whole corpus. This means very common words get downweighted, while more distinctive phrases get higher scores. After fit transform, we get TF-IDF, another sparse matrix that we'll use as our main representation for downstream tasks like naive Bayes classification and NMF topic modeling. The printed shapes confirm that both matrices cover the same set of documents with the same number of features. Only the values inside differ, counts versus TF-IDF weights. Now we layer in sentiment analysis, so the business can quickly see how guests feel in each city and channel. We use VADER, which is designed for short, informal text and works best on the raw text, keeping punctuation, casing, and emojis. The helper VADER compound runs each review or message through Sentiment Intensity Analyzer and extracts the compound score, a single number between -1 and +1 that summarizes overall sentiment. We then map that score into 3 buckets with label from compound. Anything above 0.5 is positive, anything below negative, 0.5 is negative, and everything in between is neutral. By adding 2 new columns, compound and VADER sentiment, we can compare algorithmic sentiment to the original numeric ratings where they exist and still score unrated messages like booking requests and DMs in the below table. You can see how happy reviews land with high positive scores, harsh complaints go strongly negative, and mixed or short comments often end up neutral. This gives you an immediate, scalable way to summarize mood without training a model first, and in later steps, we'll aggregate these labels by city and channel to build simple sentiment KPIs for the travel business. Now that every review and message has a VADER label, we can step back and see the overall mood in the dataset. First, we count how many texts are tagged as positive, neutral, or negative, and plot those counts as a simple bar chart. This gives you an instant, high-level sentiment dashboard. In the sample data, we see more neutral and positive comments than negative ones, which matches the fact that many guests had decent or great stays, with a smaller but important slice of complaints. In a real business, this kind of chart is exactly what you'd show in a weekly report. This week, 40% positive, 45% neutral, 15% negative. Next, we check how well VADER's labels line up with the numeric ratings. We filter to rows that actually have a rating, group by VADER sentiment, and compute the mean rating per label. As expected, negative texts hover near 1 to 2 stars, neutrals sit around the middle, and positives cluster around 4 to 5 stars. The box plot makes this even clearer. Each sentiment group has its own distribution of ratings, and you can quickly spot overlaps or outliers. For example, a 5-star review that VADER labeled neutral, or a 2-star review that reads oddly upbeat. This is a great sanity check. If the curves were all mixed together, you'd know your thresholds or domain might need adjustment. Here, they line up nicely, which means we can trust VADER scores as a useful signal for both labeled reviews and unrated messages. Now we're going to teach a model to predict sentiment directly from text instead of relying only on VADER or numeric ratings. To keep things clear, we focus on reviews that actually have a rating and temporarily ignore the unrated booking or chat messages. From those, we define a binary sentiment label. Any rating 4 or 5 becomes positive, any rating 1 or 2 becomes negative, and we treat rating 3 as neutral and simply drop it for this classifier. The helper rating to label encodes this rule, and after applying it, we filter out any rows where the label is none. The resulting review's data frame shows each review's original text, its numeric rating, and the derived sentiment label side by side. In the next cells, we'll feed the clean text version of these reviews into a TF-IDF vectorizer, train a multinomial naive Bayes model, and evaluate how well it can distinguish happy guests from unhappy ones. Essentially building an automatic, is this review good or bad, detector that can later be applied to new unlabeled feedback. Here we complete the sentiment classifier and see how well it performs. First, we vectorize the clean text for all labeled reviews using a TF-IDF representation with unigrams and bigrams. This lets the model pick up on both individual words, dirty, amazing, and short phrases, rude receptionist, super clean. We then split the data into train and test sets with train test split, using Stratify to keep the positive or negative balance similar in both splits, even in this tiny data set. Next, we train a multinomial naive Bayes classifier with a smoothing parameter alpha equals 1.0, which prevents zero probabilities and usually behaves well on small, sparse text datasets. After training, we compute predictions on the test set and print the class distribution there, so you know how many positive versus negative reviews the model is being judged on. To make the numbers meaningful, we also build a majority class baseline, a dumb classifier that always predicts the most common label from the training set. Its accuracy gives you a floor to beat. Finally, we print the accuracy of the naive Bayes model, a full classification report, precision, recall, and F1 for each class, and the confusion matrix. Even with so few examples, you can see that naive Bayes beats the majority baseline and correctly picks up most positive reviews, while struggling a bit with the small number of negatives, very typical behavior on tiny imbalanced datasets. In a real project, you'd feed it more data and maybe tune alpha, but the workflow here is the key lesson. Vectorize, split, baseline, train, compare, inspect, errors. With the classifier trained, this step is all about peeking inside the model's brain to see which words it thinks are most negative and most positive. We reuse the TF-IDF vocabulary from TF-IDF to CLF and grab the class log probabilities from CLF.feature logprob. For each class label, negative and positive, we sort these log probabilities and take the top and top indices, then map them back to their corresponding tokens with feature names top index. The printed lists show you, for example, that words and phrases like terrible, receptionist would, and bathroom clean or bathroom are strongly associated with the negative class, while phrases like great, clean, tiny clean, or night Shibuya lean toward the positive class in this tiny dataset. This kind of feature introspection is incredibly useful for both debugging and storytelling. If you see clearly sentiment-laden terms on the right side, dirty, noisy night, rude receptionist versus super friendly staff, great location, it reassures you that the model is picking up sensible patterns rather than random artifacts. If, on the other hand, you saw weird tokens like a specific city or channel dominating the negative class, that would be a red flag. Maybe your training data is biased toward one city getting more complaints, and the model is learning Barcelona equals bad instead of focusing on actual quality issues. Reading these top terms helps you explain the model to non-technical stakeholders and decide whether you need more data, better pre-processing, or different features before trusting the classifier in production. Here we zoom in specifically on the complaints and try to answer, what are people actually unhappy about? First, we filter our earlier reviews data frame down to only those rows where the label is negative, giving us neg reviews. In a real company, you'd hopefully have many more complaints. In this tiny toy dataset, we check there are at least a couple before proceeding. We then vectorize the clean text of those negative reviews using a fresh TF-IDF vectorizer with unigrams and bigrams. So phrases like noisy night or rude receptionist appear as distinct features. On top of that TF-IDF matrix, we fit an NMF model with n components equals 2, asking it to summarize the complaint space into just 2 themes. The matrices W and H are the usual NMF outputs. H tells us which words are important for each topic, and W tells us how strongly each document loads on each topic. The helper print topics prints the top words per topic, which you can then interpret in plain language. For example, you might see one topic dominated by noisy night bathroom hostel Tokyo and call it noise and facilities, and another with terrible rude receptionist recommend place and name it staff and service. Finally, we assign each negative review a topic index based on which topic in W has the highest weight and display the text alongside its inferred topic. Even with just a handful of examples, you can see how topic modeling helps cluster complaints into a few actionable buckets, which is exactly what a hostel manager needs to prioritize fixes. This final block is where everything we've built in the Capstone comes together into one end-to-end pipeline. The analyze message function takes a raw piece of text, maybe a review, maybe a booking request, and runs it through all our components. First, it calls clean text to produce a normalized version suitable for ML models. This is what will feed into the TF-IDF vectorizer later. In parallel, it computes a VADER compound score on the raw text and turns that into a VADER label, positive or neutral or negative, giving us a quick rule-based sentiment view that still respects punctuation, casing, and emojis. Then it calls extract structured info, which uses spaCy and our custom patterns to pull out a destination, the number of nights, if mentioned, and a simple room type like dorm or private room. If the clean text isn't empty, we also run it through our trained naive Bayes classifier. We transform the cleaned message with the same LF vectorizer used during training, get the predicted label, NB predicted label, and, if the classifier supports it, return the probability for each class as a small dictionary, NB predicted proba. The function then returns a compact, JSON-like summary with all the important fields: original text, cleaned version, VADER sentiment, extracted entities, and model prediction. When we loop over the 3 example messages, you can see how this works in practice. The first message about a cheap dorm bed in Tokyo for 2 nights yields destination, extracted equals Tokyo, nights, extracted equals 2, room type, extracted equals dorm with neutral VADER but a slightly positive naive Bayes score. The second message about dirty and rude staff gets a strongly negative VADER score but still borderline classifier probabilities. And the third, very enthusiastic review comes back clearly positive on both fronts. In a real system, this analyze message helper could sit behind an API and feed a dashboard or CRM, giving travel staff instant, structured insight every time a new message arrives. To wrap up this capstone, it's worth pausing and noticing how many moving parts you've successfully glued together. You started with raw, messy text and step by step turned it into a full NLP pipeline. Cleaning and normalization from part 1 gave you a robust, clean text field, which made everything else more stable. spaCy NER and simple rules from part 2 pulled out destinations, nights, and room types, turning free-form travel messages into structured fields a booking system can actually query. Vectorization from part 3 turned text into TF-IDF features, the common language that both your naive Bayes classifier and your NMF topic model understand. VADER from part 4 gave you fast interpretable sentiment scores and labels even for unrated messages, while part 5's naive Bayes model learned to predict review polarity directly from language. Finally, part 6's topic modeling helped you zoom in on complaint themes, grouping negative reviews into human-friendly buckets like noise, cleanliness, or staff behavior. All of that is now stitched together in a single analyze message function that feels like the core of a real product. From here, there are lots of natural extensions if you want to push this project closer to production. The biggest leap is to swap out the tiny synthetic data frame for a real CSV of travel reviews or messages with columns like text, rating, city, channel, date, maybe property name, and rerun the entire pipeline. You could evolve the classifier beyond simple positive or negative into multi-class sentiment, 1 to 5 stars, or even intent categories like booking request, complaint, praise about staff, and compare naive Bayes with stronger baselines like logistic regression or linear SVM. On the topic side, you might bring back LDA or BERTopic from part 6 and see how they behave on more data. At the business level, you can imagine a lightweight dashboard that aggregates sentiment and topics by week and by property, so a manager can spot trends like Wi-Fi complaints spiking in one city or staff praise increasing after training. And if you're thinking like an engineer, the next step is wrapping analyze message into an API endpoint, logging predictions, and regularly reviewing tricky edge cases to keep the system honest. As a final project deliverable, a great goal is to take a real data set, build your own notebook or mini app on top of this template, and present a few concrete insights plus a short live demo of your end-to-end Travel NLP pipeline.